Okay, welcome back. And today we are going to continue with Chapter 7 in probability. And today we're going to talk about conditional probability and also talk about independent events. So, what do we mean by conditional probability? So, if we look at this contingency table here, we've got different stocks, right? Stocks, picked stocks, and didn't pick stocks that went up. So if you pick stocks that went up versus stocks that didn't go up, used research, didn't use research. So you're uh, relating these two variables. Okay. So what happens if I want the probability that if I randomly selected an outcome, right, that the outcome did not use research. So what's the probability of not B? Well, how many ways or how many outcomes resulted in that were not did not have research? Well, it would be this plus this, right? So it would be this total. So 55 out of how many picks, right? Which would be 100. So it would be 55 out of 100. So 0.55 would be the probability, right? Or what's the probability of A? Well, the probability of A is how many ways can I get A? How many different ways can I get A? That would be 60 out of the total number of picks, which is 100. So it'd be 60 over 100. Well, what if I said, what's the probability of picking a stock that went up given that you didn't use research to pick it? Pick the stock, okay? So that given information, the fact that you know something about this randomly chosen pick, okay? The fact that you know that this pick, whatever pick it is, wasn't based on research, okay? So what does that do? Well, now that you know that information, well, are you interested in all 100 picks? And the answer is no. You're only interested in the ones that didn't do research. So guess what? Now your focus is just on this row. All the rest of these numbers you can ignore because of the new information. That's conditional probability. It's conditioned on some new information about an event that has occurred. Okay? So in this case here, now our new sample size shrunk. So now instead of dealing with 100, our sample size is now 55. Now out of this 55, how many stocks went up? 30. So now the probability of picking a stock that went up, given that the person did not use research, is now 30 divided by 55. Okay, does that make sense? So it'd be 6/11ths. Okay. And so that's conditional probability. The idea of conditional probability is that you're trying to find the probability of an event knowing that another event has occurred. And in most cases, your sample size is going to shrink. Okay. And I love doing this with contingency tables because I'm going to show you the formula, but with contingency tables and data, you never have to use the formula at all. The only time you'll need to use the formula is if they give you actual probabilities or percentages. Okay. But if they give you data, frequencies, like these here, they give you the numbers, you can just think about it. Okay. So now here's a Venn diagram that explains what conditional probability does. So let's say we have two events E and F. Okay. Well, let's say I want to know the probability of I want to know the probability of getting E given that F has already occurred. Knowing that F has occurred, what's the probability of getting E? Well, what happens is before the information, what if I said, what's the probability of E? The probability of E would be the number of elements in E divided by the total number of elements in the entire sample space, right? But as soon as I say, hey, what's the probability of E given that I know F has occurred? Well, guess what happens to the sample space? Now I'm not interested in everything in the sample space. I'm only interested in those outcomes that result in F because I know F has occurred. So I know it has to be one of these outcomes inside F. Okay? With me so far? Now I want the probability that E has occurred given that I know that F has occurred. So now, am I interested in all of E? No. I'm only interested in the number of outcomes of E that are inside F, which means I'm only interested in the intersection between the two sets. And my new sample size, or my new sample space, is now reduced to the whole set of F. And there gives us the formula for conditional probability, because it's going to be the total number of outcomes in both E and F divided by the total number of outcomes in F. And so this is the definition of conditional probability. And so in other words, it's the probability of having both E and F divided by the probability of F. And if you use the definition of probability, right, this is going to be the number of outcomes that give E and F divided by the total number of outcomes in the sample space, divided by, well, now we have another division up here. This is the total number of outcomes in F divided by the total number of outcomes in the sample space. But since this denominator is going to be the same as this denominator, those cancel, and we get, just like what I said just a moment ago, the total number of outcomes that give me both divided by the total number of outcomes in the given set, which means F, whatever's given, and this means given, this vertical line. So the way you read this is the probability of E given F has occurred. Okay. So now, if I want to know, hey, what's the probability of A given not B? Okay. Well, what's the given not B, which means, again, I'm in this row, which means I'm going to use 55 as my new denominator. That's my new sample space because it shrank from 100 to 55. And now I'm going to use 30, so it's going to be 30 over 55, right? I didn't even need to use the formula. I just thought about it, right? Well, if we use the formula, we're going to take the probability of being both A and not B. Well, what's the probability of both A and not B? Well, what's both? It's the intersection, right? It's the intersection of A, which is this one, and not B, which is this one. So these two the row and column intersect here. So that's 30. 30 divided by 100, right? So 30 divided by 100 is 0.3. Okay? And then the probability of not B is what? The probability of not B is 55 over 100. Right? Using the definition of probability, it's the total number of outcomes that give me not B over the total sample space, which is 100. So 55 over 100 is 0.55. So I get 0.3 over 55, which is the same thing as 30 over 55, which is the same thing as 611. So you get the same thing. So my point in saying this is that you don't need to memorize the formula if you just understand how to apply conditional probability. The only time you'll need to use the formula is if I give you percentages or probabilities. Then you'll have to use the formula, okay? Most of the time you're not going to use the formula if I give you like data, okay? Now here, these are probabilities, right? So if I want the probability of A just like before, I've got to add the probabilities together in A. So I've got this probability and this probability, which is 0.6, right? So I add these probabilities, and I get A, the probability of A, right? Now, what if I want the probability of E given F? Okay, so now, remember, now I'm only interested in F, right? So remember the formula. It's the probability of both E and F divided by the probability of F. Well, what's the probability of F? 0.5. What's the probability of E and F? 0.2. So the probability of E, given that F has occurred, is 0.2 divided by 0.5, which is what? 0.4. Okay? Or no, hold on. Is that right? Yeah, 0.2 divided by 0.5. Oops. Hold on. Okay. So 0.2 divided by 0.5 is 0.4. That's correct. So that would be the probability of E given F. What about the probability of F given E? Well, what's that? Okay, so here I want the probability of F given that E has already occurred. So now what happens to my sample space? Now I'm only interested in E. So now it's going to be the probability of E and F divided by the probability of E, which is 0.4. So the probability of F is 0.2 divided by 0.4, which is going to be 0.5. Okay? So the probability of E given F was 0.4. The probability of F given E was 0.5. Okay? Now, what if I'm given this, right? So here's another situation, right? So now I'm given these probabilities. So I'm going to have to use the formula in this case, right? So remember, if you're given percentages, probabilities, you're going to have to use, or fractions, you're going to have to use the formula. So the probability of E is 0.56, probability of F is 0.64, and the probability of E or F is 0.8. Okay, now find the probability of E given F. Okay, now the probability of E given F is the probability of E and F divided by the probability of F. Okay, now we got the probability of F, that's fine. But what about the probability of E and F? We don't have E and F. Or do we? Well, we don't have it directly, we don't have it specifically, but we can figure it out using the addition rule, right? Because where does and come in up in the addition rule? Well, we can use this. We know this is equal to the probability of E plus the probability of F minus the probability of both, which we don't know. But we know the other three pieces. So we can use the addition rule to solve for the and piece. So it's going to be this, or excuse me, it's going to be this. Let's see. So what we're going to do is we're going to end up taking this plus this minus this. So if we add these, we get 1.2. Okay, so 1.2 minus 0.8 is 0.4. Okay, so the probability of E and F is 0.4. Now divided by the probability of F, which is 0.64. So the answer is going to be 0.4 divided by 0.64. And so we get 5/8. And that's the answer. Okay, so now this is the product rule, or what I call the multiplication rule. And it stems from the definition, directly from the definition of conditional probability. All we do is just solve for the and piece. So if we have conditional probability, the general multiplication rule is the probability of E and F is equal to the probability of F times the probability of E given that F has already occurred. Or you can define it this way. The probability of E and F is the probability of E times the probability of F given that E has occurred. Okay. And we can also use the tree diagram to help us. And this is where the branches, the rule that we're going to use, when you use the tree diagram, you multiply down the branch and you add across branches. Okay, so each branch, if you're going to go down the branch, then you're using the multiplication rule. If you're going across branches, it's the addition rule. Okay, so if I want the probability, so here's as far as the way we'd use this, so executive, campaign, branch, and probability. Okay, so here's the executive, here's the campaign, right? So here we either have this A or B, right? So here's the probability of B, here's the probability of A. And then we also know the probability of S or U. So 3/4 is the probability of S, 1/4 is the probability of U. So notice how these add up to 1 and these add up to 1. Okay. Now, if I want to know what's the probability of having A and S, that would mean that I'm going down this branch because I'm going down this decision tree, right? So down this tree, I have A is the outcome, and then followed by S. So the probability of A and S is going to be 2/3 times 3/4. Because if you think about it, it's the probability of A times the probability of S given that A has occurred, right? This is the probability of S given that A has occurred, right? Because I'm going down the A branch. Okay, so it's going to be probability of A times the probability of S given that A has occurred. So it's 2/3 times 3/4, which is 6/12, which is 1/2. Okay, so the probability of A and S is 1/2. Now what about the next branch? What's the probability of A and U? Well, it'd be 2/3 times 1/4, which is 2/12, which is 1/6. Okay. What about B and S? What if it's the probability of having B and S? Well, it'd be the probability of B times the probability of S given that B's occurred. Well, that's this. So it's going to be probability of B plus the probability of S given that B's occurred. Okay, so it's going to be 1/3 times 2/5, right? Which is going to be what? 2/15. And this is going to be, for the last one, it's going to be 1/3 times 3/15, which is 1/3 times 3/5, which is 3/15, which is 1/5. Okay. And notice that the probability of all possible outcomes for each branch. So there are 4 possible outcomes total. You can have AS, AU, BS, or BU. And so if you add up all of these probabilities, they sum up to 1. So the cool thing is the tree diagram gives you the probabilities of all of the possible outcomes. And notice that they're not equally likely. Okay. These outcomes are not equally likely. Okay, and this is using the product rule, the multiplication rule. Okay, now what if I wanted the probability of B, let's see, what if I wanted the probability of the probability of let me think. The probability of B or U. Probability of B or U. Well, that means, well, if I use the rule, it's going to be the probability of B, right? Well, what's the probability of B? Well, I have the probability of B would be either, the probability of B is 1/3, right? But I have S or U here. So I would go down, the probability of B would be this, well, would be 1/3. Or the probability of U. Well, the probability of U is going to be this branch or this branch. So if I want the probability of U, in this case here, I'm going across branches, which means I'm going to have to add these two probabilities. So it's going to have to be this one plus this one, which means it's going to be 1/6 plus 1/5, which is going to be what? It's going to be 11/30. Okay, so then I'm going to have 11/30 plus B, which is 1/3, but then I'm going to have to subtract off the probability of both, which is going to be this branch here. Okay, so again, you can use the branch for the addition rule and the conditional probability or the multiplication rule. Okay, you don't have to though. Okay, so let's use this tree diagram. Let's say we have the first plant, we have these three. We have C, LA, and New York. So these are the three locations, right? Okay, so we have these, the first plant here. Then we have the second plant is here. So first plant, and these are the options, C, LA, New York. Okay. I'm not sure what C is. Is that, yeah, I'm not sure what's going on here. I think these are locations. And then the second plant, and these are the same locations, right, except these last two. Okay, so the second plant, so what are our total outcomes? We have 8 possible outcomes. Okay, so now, what do we do here? So, what is the probability of C getting a C and a C? That both plants are located in C, wherever that is. So in this case, we're going down this branch, and so it's going to be 1/2 of 2/5, which is 2/10, which is 1/5. So this will be 1/5. And the probability of this, they already did, which is going to be again 1/5, because these are the same. And then this is going to be 1/2 of 1/5, which this is going to end up being 1/10. So far we got 1/5, 1/5, 1/10. Now what about this one? The next one is 1/5 because we're going down this here. Now what about this one? Okay, 1/3 times 1/5 is 1/15. Okay, in fact, both of these will be 1/15. And then this one's going to be what? 3/30 or 1/10. And this one is going to be 2/30 or 1/15. And so if you add up all of these probabilities, they will add up to 1. Okay, now what about this one? So heart or not a heart? Second choice, red or black. So these are the cards. So this is a standard deck of cards. So we have a first choice. So first draw, second draw. Okay? Now notice, you can see this is conditional probability. There's what we call without replacement. So you're taking the card out and you're not putting it back in the deck. Okay? So, or you're drawing 2 cards, one right after another, and you're not putting the first card back. Okay? So every time you take a card out, the number of cards in the deck goes down by 1. So in this case here, the first probability, the probability of getting a heart on the first draw, well, how many hearts are there? There's 13 out of 52. And so how many cards are not hearts? Well, the other 39 out of 52. Now, after you draw a card, this is the first card. Now how many cards are in the deck? Well, there's only 51 cards. Notice that the probability, it's now only 51, not 52. So notice the denominator went down by 1. So now, on the second choice, what's the probability of getting red? Right? If you got a heart on the first draw, well, how many how many red cards are in the deck? Well, you got to understand, a heart is a red card. So if you drew a heart, you also drew a red card, which means there's not 26 red cards, there are 25 red cards in the deck. Okay. So that means the probability of drawing a red, given that you drew a heart on the first draw, is 25 out of 51. Or the probability of drawing black, well, if you drew a heart, you drew a red card, which means you did not draw a black card, which means there's still 26 black cards in the deck, so it's going to be 26 out of 51. And notice these two numerators add up to 51. Okay? So these two probabilities add up to 1. These two probabilities add up to 1. Okay? And what about these? Well, what's the probability of getting red? If you didn't get a heart here, okay? If you didn't get a heart here, what's the probability of drawing a red? Well, how many red cards in the deck? Well, if you didn't draw a heart, okay? How many red cards are in the deck? If you didn't draw a heart, well, how many hearts are in the deck? There are 13 hearts. They're all red, right? You know that you have red cards, the hearts and the diamonds are red. Well, if you did not draw a heart, that means 13 cards are off the table. That means how many red cards are there that you could have chosen? Well, only diamonds. So there are only 13 red cards. Oh, hold on a second. Hold on. Okay, hold on. If you did not draw a heart, yeah, I'm sorry, I misunderstood. So if you did not draw a heart on the first draw, well, that means you still have how many hearts to pick from? Well, you still have 13 hearts, right? Because you didn't get a heart. So that means how many red cards are there still in the deck if you know you did not pick a heart? Well, this is where it gets a little tricky. Think about it. Okay, so you did not get a heart on the first draw. So you still have how many cards in the deck on the second draw? 51. How many of those cards in the deck are red? If you know you didn't get a heart. We don't know. That's the thing. I don't know how many red cards are in the deck because I could have gotten a diamond. Okay, I could have picked a diamond on that first draw. Okay, but if I know I didn't get a heart, so it's kind of hard. So I can't figure out these two probabilities. Okay, so sometimes the tree diagram doesn't work because just because I know I didn't get a heart doesn't mean that I know how many red cards are in the deck. on the second draw. I know how many. I know there are only 51 cards, and I know I didn't get a heart. Okay, so yeah, I'm not sure you can figure this one out because you don't have enough information. Okay, so you have 39 cards, right? So that are not hearts. Oh, hold on a second. Hold on a second. Oh, yeah, 39 cards. So on the first draw, you did not get a heart. Yeah, so that means there are 39, so 39 of 52, okay? But then on the second draw, the probability of getting red on the second draw, yeah, don't know. Oh, wait a minute. Oh, this is a different one. Yeah, okay. Now in this case here, now if we do it this way, now we can fill it out because we know red and black and we're doing red and black. So now if we do it this way here for this example, then yes, we can figure it out because we know that getting a red on the first choice, because now we know there's 26 red cards and 52 cards total, and we know there's 26 black cards with 52 total, so we know it's half and half, right? But if we get a red after the first choice, again, without replacement, because we're not putting the card back, right? So this is conditional probability. Then what happens is on the second choice, now what's the probability of getting red on the second card if I know I got a red on the first draw? Well, it's going to be now 25 red cards out of 51 because I drew a red card. So now the number of red cards went down by 1, and the number of cards in the deck went down by 1. And then the probability of getting black, if I got a red card in the first draw, is now, well, there's still 26 black cards in the deck because I drew a red, not a black on the first draw. So there's still 26 black cards out of 51. And then if I come down here, if I drew a black card on the first draw, well, the probability of drawing a red is 26 out of 51 because there's still 26 red cards in the deck when I draw my second card. But if I want the probability of getting a black card, given that I got a black card on the first draw, well, that's going to be 25 out of 52. Okay, so the probability of getting a black and a black is going to be 1/2 times this. The probability of getting black and red followed by red is 1/2 times this. The probability of getting red followed by black is this times this. The probability of getting red and red is this times this. That's it. Now, independent events. When two events are independent, all that means is that the probability of one event occurring is unaffected by the occurrence of the other event. Meaning that, hey, whether an event occurs or not, it doesn't affect the probability of the other event. So two events are independent if the occurrence of one event doesn't affect the probability of the other event occurring. If I have 5 events, all 5 of them are independent if none of them are affected by the occurrence of the other. The probabilities remain the same. So in other words, it doesn't matter. If F and E here are independent, it doesn't matter whether I know that E has occurred or not. I still get the same probability. The probability of F is the same. So the probability of F, given that I know E has occurred, doesn't change. It still is the probability of F. Or the other way around, the probability of E, given that F has occurred, is just the probability of E. So the probability of E doesn't change. This is the definition of independent events. Both of these conditions must hold for it to be independent, okay? And so, if they are independent events, we get the simplified multiplication rule. And what it means is just like with the addition rule, we have a general addition rule, which means we have to subtract off the intersection, right? It's the probability of E plus the probability of F minus the probability of both E and F, right? But if they're mutually exclusive events, then the intersection goes to zero, and it's just adding their individual probabilities. Well, the similar thing happens with the product rule. In the general case, we have to consider conditional probability, right? In the general case, it's the multiplication rule, we have to consider the conditional probability. But if E and F are independent, well, guess what? This just becomes E. And over here, this becomes F. And so if they're independent events, we get this multiplication rule. So it's just the multiplication of their individual probabilities. And that's it. And so now, make sure you practice. And next time we're going to consider Bayes' theorem. Bayes is a very famous theorem, very famous person who did a research he was a statistician. And so we're going to talk about Bayes' theorem. And that's going to be a very powerful theorem. It's going to involve total probability and some really neat examples that we can use Bayes' theorem. Okay, so until next time, have a great day.